Thank you for giving us the chance. I'm Jayamine Alupotha. So I'm going to present our joint work with Maria Rosaria, Yanis, Abmanu, Christian, and Fan. So the paper title is Anonymous Self-Credentials and Application to Single Sign-On. So this project originated in 2024 IC3 hackathon and it turned into a paper. So let me ask you a question. Why do most online accounts require an email address or a phone number? So the answer is that they want CB resistance. In that, because when you create an account, they have to allocate resource for you. But the problem is that if one person creating multiple accounts, then they have to allocate more resources, so they want to optimize it. So because of that, they usually ask for an email or a phone number, so they can uniquely identify you. So in real world, we have different ways to obtain CB resistance. One could be financial constraint. For example, you have to pay for an identity, or it can be a time limitation because, for example, if you think about an email, you have to go and create multiple emails. So it's kind of time consuming. And then also another strong way to like obtain CB resistance would be trusting some kind of identity provider. For example, like having a driving license. So you need a driving license per one account. So it's a very strong way of obtaining CB resistance. So, in other words, if we simplify this one, Sibyl resistance means that it's a again by limiting the number of identity one person can have, or it can be one identity, or it can be fewer identity. So, in a traditional case of Sibyl resistance, what happens is that you are kind of forced to use a master identity, and then you have to use the master identity in multiple with multiple service providers. For example, you have to use it with ChatGPT, Instagram, or Amazon. So what happens is that then they can they can gather data about yourself, and then they can share this data with other service providers. So this kind of creates an entire profile of you, which you did not know. So what we can do is that we have to what we can do is that instead of giving your master identity like your email address, we can give different pseudonyms for to different service providers. So this limits the how data is shared, because now we are using different pseudonyms. uh, for example, Apple, they instead of giving your actual Apple email address, they can generate multiple email addresses for you, and the service providers won't be able to link you across services. However, the problem is that the person who generates these pseudonyms can link you. So if this the identity provider is malicious, then you don't actually have privacy. So also there are other solutions, especially decentralized solutions. So in these decentralized solutions, instead of a single central provider creating these pseudonyms, there is like a community of service providers generating them. So the main idea is that we want to avoid the single point of failure. However, it doesn't do anything regarding privacy, because even a single member in the community can actually link your identity. So in these scenarios, what happens is that you have this identity provider who is trying to offer you privacy, but the privacy. So if the identity provider is malicious, then you don't actually have the privacy. So the question is that, can we get rid of the identity provider? So if we get rid of the identity provider, then we have two questions. The first one is we want severe resistance for the service providers, and also we want usability for the users. So if we don't have identity provider, can we can we obtain the severe resistance and also usability? So the question that we actually explore this paper is that, can we use cryptography in order to do that? So before explaining our solution, let's identify what we actually want to do. So the setup that we have for our this our setup is that we have two types of users. The first one is we have actual users, and then we have service providers. So the users have a secret key and a master identity. So here and then service providers also have some kind of a name that we can uniquely identify them. um, so the first thing is that user should be able to register a pseudonym with one of the service providers. And so, however, the service providers should not be able to identify um, which user which user created this pseudonym. So for that one, we actually collect all the master identities, which we call the anonymity set. So the service providers see that one of the identity in the anonymity set created it, but not which one. So, and the second one is that we want Sibyl resistant. It means that if the same user wants to register two different pseudonyms for the same service provider, then there should be a way that the service providers can link these pseudonyms, say that, okay, they don't identify which master identity created it, but they can identify that the same master identity create both of them. So, which gives them the CB resistor. So in our in our this framework, we have four functions. The first one is the setup, and then we have the generation function, which allows users to generate master identities and secret keys. And then we have two functionalities. The first one is proof. So let me explain. So the proof function take the all existing master identity, which is the anonymity set, and then it also requires the secret key of the user, and also the pseudonym that the user wants to register, and also for which service provider. And then this proof function generates two outputs. The first one is basically a proof, and then it also generates something called nullifier. So the idea of the nullifier is that if we have the same secret key and the same service provider name, then the nullifier should be unique. So it doesn't matter which pseudonym we are using. If the secret key and the verifier name are the same, then the nullifier will be unique. And then the verifier function basically takes everything and outputs whether the proof and the nullifier are correct or not. So now in the target scenario is that whenever user wants to registers or pseudonym, the user sends this proof and the nullifier to the service providers. And the service providers, they verify this pseudonym, these three items, and then the verifier stores these nullifiers in their memory. So if the nullifiers stores these nullifiers, and if this user tries to register another pseudonym for the same verifier, we said that the nullifier will be same. So the service providers can identify that the same person is trying to create another account, and they can decide to reject the second pseudonym. So if they they can also have some kind of like a weird properties like that. So for each identity, we allow two pseudonyms. So in that case, they will reject the third one. So the basic idea is that if the user tries to register multiple times, the nullifier will be still the same, allowing the service providers to identify them. So now, Next, we need to actually look into the cryptographic security properties we want with this scenario. So we have 6 properties. I will spend some more time going through these properties because I think it's a little bit important for your hackathon. So the first property we want is the correctness. Correctness basically says that uh, any like honest prover should be able to self-generate valid proof and nullifier for any pseudonym for all verifiers. And the second part of the correctness is basically that um, if we the nullifier should be different if the users are honest. So because if me and somebody else have the same nullifier, then one of us cannot use the same service. So we want to avoid such thing. And the second property we want is robustness. It basically says that the malicious provers cannot hinder the pseudonym registration of honest provers. So even if all the other provers are malicious, the honest prover can still register with services. And then we have the SEBI resistant. So if you want to formalize SEBI resistant, we assume that all the provers are the users are malicious, and then they work together to create different nullifiers, but originating from the same secret for the same verifier. So they should not be able to do that. And so then we need unforgeability. So unforgeability is a little bit complicated. The first property we want from unforgeability is that yeah, like attackers should not be able to forge a proof for using honest prover's identity. So that property is very straightforward because I don't want somebody else using my identity to register for a service provider. But also, if you think a little bit more about it, so what if the other service providers are malicious? For example, like I want to register with Amazon, but I also had registered with ChatGPT and Instagram. So they are malicious and they work together to steal my identity. So still, they should not be able to do that. And but it doesn't end actually there, because if you think about real world identity, so you cannot actually have any pseudonym that you want, because somebody might have already used that pseudonym, or the service provider can decide this pseudonym is too long or too short. So service providers can actually put some restrictions on your pseudonym. So in unforgeability, we actually want that even if this malicious service providers select which pseudonym that the honest prover going to register, there should not be forged proof for another service provider. So the unforgeability basically says that others cannot steal your identity even if the other service providers and other users are malicious. Okay, so for the privacy, we have two properties, anonymity and unlinkability. So the anonymity basically says that, let's say there are only two honest provers and all the other users are malicious and all the service providers are malicious. So in this case, if we generate a pseudonym and proof and nullifier, the service providers should not be able to identify which honest provers actually generated. So we need at least two honest provers, because then we so, two honest provers, because even in that case we still have the anonymity set of two. And however, as I said before, we don't have the luxury to choose any pseudonym we want. So sometimes pseudonyms will be chosen by the service provider. So even in such case, the service providers should not be able to identify which identity or which user created the proof and the nullifier. So as I said before, so this is for a one pseudonym. So what will happen if there were multiple failed attempts to register? So even if there is like a series of attempts with different proofs but with the same nullifier, service providers should not be still identify which secret key or which user is trying to register with them. So the second privacy property that we want is unlinkability. So unlinkability says that if there are two honest users and there are two proofs, nullifiers, and pseudonyms, the malicious verifiers should not be still identify whether these two pseudonyms are coming from the same identity or from different identities. So if they cannot link or link them, then we can basically then we can basically say that the protocol is unlinkable. So these are the 6 properties we want to obtain, and the we identify that there are multiple cryptographic protocols that are already implemented actually provide these properties. So one of them is traceable ring signatures. Then also there are other snark circuits for anonymous messaging also provide these properties, and also double-blind proof of existence. So if we have all these 6 properties in another construction, you can also use that construction for anonymous self-credential. Now, the next slides, I am going to explain how we can use these anonymous self-credentials to build a single sign-on protocol. So, single sign-on basically says that we can use one email address, or we can use some kind of a master identity for different service providers. So in anonymous self credentials, we are going to use the master identities in anonymous self credentials to sign on. So we have 3 components in this use case. The first one is we have users. Each user has a master identity and a secret key. And also we have a immutable identity registry. So immutable identity registry holds verifiers or the service provider's name and also all the master identities of users. So this registry could be a blockchain. Also, it can be a smart contract that stores these values. So, and this registry, the only thing that we want from this registry is that it should be immutable, and also it should have some kind of a severe resistant onboarding. For example, in our case, what we are doing is that users have to pay in order to store their identities. So, and once so when a user wants to register a pseudonym for or register for an account in one of the service providers, what they can generate a pseudonym, and then they can send the proofs and nullifiers to the service provider. However, this is actually a naive solution, because if you think about it, not only when we register but also every time we log in, they have to generate these proofs and the nullifier. So generating proofs is somewhat costly, so we want something little bit more optimized. So we introduce user issued unlinkable SSO, or simply U2 SSO. So what we propose is that instead of registering pseudonyms, users can register child credentials. For child credentials could be your public key and a pass key, and also it can be simply your username and a password. So once you register, once you generate the child credentials, instead of sending the pseudonym, they send the child credential to the service providers. So once they register, they can use that child credentials to prove the ownership. So every time when they log in, they don't have to generate proofs. They simply can use these child credentials. So we have different, we have two U2SSO constructions. They use different anonymous self-credential. One use SNARK protocols, the other one use double-blind proof of existence. They have different protocols. For example, double-blind proof of existence use a transparent setup, and also it has some kind of proof size is a different like a login with the L. L means that it depends on the number of service providers you have. However, in a SNARK circuit, the proof size does not depend on the number of service providers. And also, if you can change the anonymous self-credential protocol, you can build a new U2SSO protocol. So I will skip this, and so this is basically the interface for U2SSO implementation. Users can generate their child credentials, for example, user name and a public key, and then they have to provide the anonymity set size, nullifier, and the membership proof, which is basically the proof that I previously mentioned. And when they want to log in, they simply give the child credential, and then in this case, they are using a public key, so they have to give the digital signature. But if they are using a username or a password, then they, instead of a digital signature, they may have to put the password. So to summarize everything, we talked about initially we talked about federated SSO. So in federated SSO, usually the users have to interact with the identity provider every time they log in. And also, the users are restricted to use the child credential scheme that the identity provider has selected. And also, this protocol offer privacy. Basically, you have to rely on the identity provider if you want to obtain privacy. However, in U2SSO, we have minimal interaction with the identity register. And also, the users can decide which anonymous self-credential scheme and the child's credentials that they want to use. And also, this is a user-centric private. This is user-centric privacy, and uh, so you can find our GitHub repo here. And thank you. Also, for your hackathons, you can either use U2SSO in different application, and also you can try to build new anonymous self-credentials. And also probably you can identify more use cases of anonymous self-credential by tweaking the protocol in different ways. So, and I also wish you good luck. Thank you.